Hello again. So we have been discussing LTI systems, and we have one small topic left behind in this second chapter. That is regarding although we have done some tutorial problems wherein we try to have a implementation of some LTI systems. I think we did it in the at the end of the chapter one. So there is a typical way of expressing, representing our LTI systems, for that matter, any system in terms of some basic building blocks. Although representations are different, we have block diagram representations, we have signal flow graphs, we also have data flow graphs. But one of the most frequently used representation is that of block diagram representation, wherein your system, which is expressed as a transformation of an input signal, and the different operations that relate to that transformation are represented using small block diagrams. Fine. So a block diagram is basically it's an interconnection of some elementary operations that act on the input signal. So if you remember our first definition of the system, let me first complete it. And the way we defined this system was something related to this. So it's basically a series of operation. Yeah, you can define a system as a transformation which consists of a series of operations that act on the what you call input signal. So block diagram representation is just you can say a kind of a graphical or a schematic representation of those operations. Like I said, we have done some problems wherein, if you remember, we did a cascade implementation, we did a parallel implementation at the end of our first chapter, and Wahapi we used some blocks. So here we will discuss it in a more formal way, that what kind of blocks we can use while going for the block diagram representation of a particular system. Fine. And we have typically the analysis that we have conducted so far in the with regards to LTI system, it has been in terms of impulse responses. Right? We have expressed our signal input as a sum of impulses. And then we have done some analysis and we have done the characterization. Now, block diagram representation, it consists of interconnection of three elementary operations which we often use in representing our system. So there are three elementary operations, and your system is basically an interconnection of these three elementary operations, right? So the operations are, we have the scalar multiplication, wherein mathematically the operation is defined as something like this, that your output y of t is some scalar constant, say c, multiplied by the input signal x of t, right, in the continuous time domain. Or if you're talking about the discrete time domain, it is y of n is some constant c into x of n, right? Where c is a scalar quantity, right? And if we are going for the block diagram representation, it will be represented like this. So at the input side, you will have x of t, x of n, as the case may be. And you will represent a simple line with an arrow, something like this, and the constant c. And this is a representation, block diagram representation of this operation. Right? A simple line with an arrow, it kind of is a gain factor, and you represent what is the amount of gain on top of that line. Right? Then our second basic operation is that of addition. So again, in the continuous time domain, the operation may be something like this: y of t is equal to x of t plus say w of t. Yeah, if you're talking about the discrete time domain, y of n is equal to x of n plus some another signal, discrete time signal, wn. Fine. So for this representation, we have this kind of a block. You have a summation. On one side, you have another signals. It may be x of t if you're talking about the continuous time domain. Yeah, x of n. And then on the other side, we have a second signal, wt for continuous, yeah, wn. And in output, you'll have y of t, which will be the sum of these two signals. And similarly for the discrete time domain. Then we have third one, scalar multiplication addition. Then we have integration. If you remember, integration we normally use for continuous time systems. Fine. So for a continuous time system, it will be something like this: y of t is equal to minus, जो भी integral है, whatever the limits are, x of tau, t of tau. Fine. And so we will be representing this as x of t. Then we'll be passing this through a block wherein we'll be using this sign. This represents an integral. And then you will get y of t, which will be defined by this equation. Okay. So integration, differentiation, yeah, differential equations. So they have it demands continuity. I mean, you can only apply differential. You can define a differential equation for continuous time variable. Discrete time, we have the counterpart, what we call the difference equation. Fine. So difference equation is something like this: y of n is equivalent to x of n minus 1, which you know it is basically a time shift operation. This is again one commonly used block that we use to scale. Here we have x of n, then we have different representations. Typically we use s. It will give a, again we have used this block if you remember in chapter 1, so it will be something like this. So these are some basic building blocks using which we can have a block diagram representation of our system. Right? It's a kind of a graphical representation of your system. There are many other forms. There are, like I said, signal flow graph is one that is frequently used. We also have the data flow graphs. It depends upon the type of analysis we are doing. But in this course, wherever required, we will be mainly relying on the block diagram representation. So this was a small topic that was left in the LTI systems. And before we start the new chapter, obviously we will be doing a small tutorial session. We will be having a live interaction. But I would like to summarize what we have done so far in the first two chapters. So our first two chapters, it was basically, especially the second one, it was basically the time domain analysis. We defined our signal in the time domain. This was the point where from it started: x of t, t is the time, or if it is discrete time, x of n. But it was in the time domain itself. Our signals were defined as the continuous, discrete variables that depended upon the time, either in the continuous or in the discrete domain. And then we did, in the first chapter, we did some basic operations that wherein we developed some fundamentals of signals. We also discussed certain classification of signals. What is a periodic signal? What is an energy signal? What is a power signal? What is an even signal? What is an odd signal? and every classification was based on some property. From there on, we studied some elementary signals. We studied impulse signal. Impulse signal was an important signal that we used actually in chapter 2 to define our LTI systems. We also studied exponential signal. We established a relationship between a complex exponential and a sinusoidal signal. So all those things we did. Then we moved on to systems. Again, we defined system in the time domain. Our input was a signal in time domain, whether it was a function of continuous time variable or discrete time variable, but it was in the time domain. Then we again discussed the properties of the systems. We discussed what linearity means, what stability means, what causality means, what time invariance means, and these properties. And with these properties, that was our first chapter. Then we used these concepts, some of these concepts, in the second chapter, where we defined a special class of systems known as the LTI systems. That's the systems which are linear and time invariant. We did some analysis, and an important part of that analysis was we defined our signals in terms of impulse signals. This is an important point. So you had an arbitrary signal x of t. You defined this signal in terms of the impulse, which was delta t, not actually equal to x of t was kind of defined in terms of delta t. Right? And this is an important, this was basically the starting point of our LTI system analysis, जहाँ पे आपके पास you have any arbitrary signal x of t, and you can very well define it in terms of what you call the impulse signal. Fine. And based on this particular starting point, we then, to be precise, it was something like this: x of t delta t minus tau deta for the continuous time domain. And we had a corresponding equation for the discrete time domain as well, which was in terms of which was a simple summation, something like this. I don't exactly remember what the exact form was, but the basic point here was that we were expressing our input signals, whether a continuous time domain, a discrete time domain, in terms of the impulse signal. This was a very important point. And then we did the analysis. We came up with a condition for stability and causality. For causality, we had that the impulse response should be less than 0 for n less than 0. And similarly for stability, your impulse response should be absolutely summable. So two things are here. First, we expressed our input signal in terms of impulse signal. Then we expressed the properties of these systems in terms of the impulse response. Fine. So this is an important thing. And whatever analysis we did, it was in terms of, it was in the time domain itself. Okay, so there's a kind of a, x of t या जो भी आपका signal था, it was expressed in terms of delta t. Then यहाँ पे भी t था, यहाँ पे भी t था. So even in this conversion, everything was done in the time domain. Fine. Because when we discussed the elementary signal, impulse signal, whether it was a discrete time case or the continuous time case, it was purely defined, it was purely discussed in the time domain. इसमें frequency का कोई concept नहीं था. ठीक है? Now henceforth, when we start with the third chapter, we have 3 more chapters, third, fourth, fifth. The analysis will now shift to frequency domain. Right? And you will see we'll be kind of following the same methodology. Only difference will be we will be doing it in the frequency domain. Right? Now we have a lot of elementary signals that we discussed. We discussed unit step. It was entirely discussed in the time domain, u of t, u of n. We then discussed what you call impulse, delta t, delta n. Right? We discussed ramp, r of t, r of n. But there were two signals wherein there was a concept of frequency. We had the sinusoidal signal cos omega t. Omega was the factor that basically defined the frequency. Fine. Then we also had the exponential or the pure exponential or the complex exponential signal. Maybe we had e raised power j omega t. So concept of frequency was observed in these two signals, the sinusoidal signal and the complex exponential signal. So although we will be discussing in detail, but it's a kind of that embellishment that if we are going to do the frequency analysis of these signals and systems, it has to be in terms of these sinusoids and exponentials, complex exponentials to be more precise. Right? And this is in fact the case when we will go to the frequency analysis. You will be seeing that we will be expressing our signals. जैसे यहाँ पे we express it x of t in terms of the delta signal, delta impulse signal, delta t, delta n. We will be expressing our signals in terms of sinusoids, yeah, complex exponentials, because we have also established a relationship between a complex exponential and a sinusoidal signal. So either way around, whether you expressed it as a function, yeah, as a series of sinusoids, as a series of complex exponential signals, both the cases there will be a concept of frequency. Okay? So henceforth, from third chapter onwards, we will be doing the frequency domain analysis. So we will be expecting, since we have defined two signals, the sinusoid signal and the complex exponential signal, we have defined these signals, and these signals give some insight, have the concept of frequency. Again, like I said, हमारा जो साइन सिग्नल था या साइनोसाइड, it was typically expressed as a cos omega t plus phi, where omega is the angular frequency. So there is a parameter in this signal which relates to frequency. Right? Similarly, when we did the complex signal, it was something j omega t. Again, omega is involved. So we are expecting in the frequency analysis that we will be expressing our signals in terms of these sinusoids and in terms of these exponentials. Right? So future videos will be about the WAPE. We will study this in detail. How do we express our signals in terms of these, and how do we convert our analysis? Yeah, how do we actually transform from the time domain analysis into the frequency domain analysis? And you will see a lot of symmetry. जैसे यहाँ पे हमने analyze किया, we first characterized, got the mathematical formulation of our system, then we expressed the properties of the system in terms of those formulations. We'll follow an exact sequence, exact methodology in the frequency domain. First, we will introduce some brief concepts. Fine. And once we are done with the characterization, we'll be again interested in the stability, the causality, the way they are expressed in the frequency domain. So you will get alternate definitions, you will get alternate conditions of causality, stability in the frequency domain. Okay? So I'll stop here, and next videos we'll be starting with the frequency domain analysis.